You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics, such as energy. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. At the beginning of 2022, Worth Electronic teamed up with Emser, and we presented a joint webinar on how to pass conducted emissions using line filters. The idea was to start with this theory and basic methodology of implementing a power line filter to reduce conducted emissions. It was then tested with live measurements and is based on the strategy to separate differential and common mode components, showing how to select an optimum filter to pass the tests. In today's podcast, we'll demonstrate the effectiveness of model separation by theoretical approach and explain live demo experiments. Enjoy today's What's Up podcast with Worth Electronic and Emser, how to pass conducted emissions using line filters.
My name is Laurent Völkel. I'm working over 22 years with Worth Electronic, and today I will talk a little bit about some basics, I will say, and some tips and tricks during EMI measurement when you make special conductor emission measurement. There are some helps, and sometimes you want to know what's happening, and I will try to explain that from my point of view. So first of all, conductor emission happens mostly, of course, when you have a switched mode power supply. You have to pass with the switched mode power supply, the conductor emission, and also, of course, radiated. But if you take a look on typical, is simple, I would say, simple switched mode power supply, which is galvanic isolated. It's, I guess, the flyback is the most common one. It's very simple. Of course, it's using a transformer, and the typical usage is for power mostly less than 100 watts. So already for 100 watts, you can try to use LLC or even different other topologies. The advantage is that it's very easy. It's not so complicated. It's quite very easy to make your circuit working. The bad thing is that really, if you don't take care on flyback topology, you may have a lot of disadvantage in terms of EMI. So you need to make a good filtering on the input if you want to pass conductor emission. Mostly what is happening, everybody think, okay, the responsible component which make the problem is a transformer. I would say this is a half true, because yes, with the transformer design, you can improve or you can damage. Of course, it's also, I would say it's how much you pay for the transformer. Because a very cheap transformer, you may have also free of charge lot of parasitics, of course, and you have to pay for the EMI a little bit more later on. What we can do for a kind of transformer, actually take a little look on the transformer, and we will see that when we are switching actually on primary side, switch on and switch on, we try to transfer this energy from primary, from this high voltage to low voltage, or for low to high voltage. Mostly we transfer this electrical energy into magnetic field. We store this magnetic field into the core, and on the secondary side with different number of turns, so the turns ratio different, we take out from this energy, which is now magnetic field, and make again with the induction kind of power supply, step down or step up. But we have a noise which is coupled from primary, from secondary to the primary, and with this noise which is coupling through, because even it's galvanic separated, it's happening because you have a parasitic capacitance between these two winding, primary and secondary. What we can do with this noise, because we have to accept that there is a capacitor between secondary and primary, even we don't want to have them, we can put by ourselves a capacitor, because just to decrease the winding to winding capacity is not so, I would say, it's very expensive and not so easy to do it. So what we can do, it's very easy. Take a Y-cap capacitor crossing the transformer, and hopla, that was too much clicks, and put this Y-cap capacitor for the primary hot point for the highest voltage to the secondary negative or ground, whatever. But this capacity must be very, very close located directly on the transformer legs. When you put first this transformer, this value should be in nano, very, very low pico and nano, maximum 4.7 nano range, and should be, of course, kilovolt withstand. And you will see on your EMI measurement machine or spectrum analyzer that you will have noise, of course. But now you are the boss of this noise. You can control this noise with the capacity where you can shift it. The winding to winding capacity is a parasitic accidentally which have you no control. If you put this capacitor, with this capacitor you can guide this noise in the area where you can do your own filter. So if we just decrease and we are focusing to decreasing by the winding to winding capacity, it could happen that we can decrease the winding to winding capacity instead of put primary and secondary above each other. We can put one winding and second winding on the core separately to each other. It's very good distance for safety margin as well. But what will happen? It will happen following. You decrease the winding to winding capacity, but you increase enormously the leakage inductance. Now you don't have to fight for the capacitor, you have to fight what I'm doing with the leakage inductance. You have to make an excellent good snubber, but you destroy in a snubber effectively energy. So this energy doesn't come from a parallel universum, it will cost for your efficiency. And the best thing what you can do, it is always a balance between not too high winding to winding capacity, but not too high leakage. Something in the balance, like in the nature, is very good. How to do this? Not so easy, I know. I can show you something here which is made with a demo board. This is a very simple demo board. You can see here is a transformer. We have here a common mode choke on the entrance. Here's the snubber. Here is Y-cap, which is from primary to secondary. We have some output filter. And this is a very simple design with a link switch. Okay, what we did done first, we find out that if we use in our transformer kind of potting or varnish, some potting material, we find out by the same transformer, the same design, mechanically absolutely identical. The only one thing in one, it was used potting material, the other one without potting material because we want to experiment. We find out as soon we get off of this potting material, which with a potted transformer, we did not pass the EMC test and we failed. This is conducted emission. No, sorry, this is radiated emission. In this case, it's radiated emission. We find out that as soon we take out this potting material, look what will happen with the same construction, only just changing not the transformer, just the same transformer without potting material. We passed the EMC test. So because of that, we decide to don't increase this the electricum into the transformer and don't use varnish or potting material into the transformer because that may cause also some negative EMI solutions. Some noises. Okay, what we can do, we took again this demo board and we adjust the snubber of the best effectivity what we can do, and we did not use the Y-cap, we did not use the common mode choke, and we start to measure common quasi-peak and averaging measurement, and we found very fast that we did not pass the EMC test, so there's a lot of noise. So what we are doing first of all, of course, we put the common mode choke because the common mode choke is a good filter. The snubber is adjusted, introduce the common mode choke, and wow, exactly expected, the common mode choke does his job. But if you look to the test result, we find out, okay, it still failed. It's not so good. So the next step, what we did done, we took this Y-cap, this crossing Y-cap above the transformer, and we adjust this value to exactly in the maximum of the common mode choke impedances, and then ta-da, we passed the MC test. So now you can congratulate yourself. You're a good engineer. You passed the MC test. But we waste a lot of time with this snubber adjusting. So how about if we take just the snubber which is in the reference design from the application note or demo board from the IC manufacturer. So we took back to the simple snubber, and we find out as soon we change the snubber in this constellation, but we leave the Y cap and the common mode choke, it is increased a little bit this noise, but still pass the MC test. So now it's up to you. If you have time, you can readjust your snubber or just take the standard snubber which is recommended from the IC manufacturer. So sometimes it's not so good. So conclusion, you have to put on flyback topology for sure a common choke. You have to put a Y cap, but it's not always necessary to work on this snubber. If you want to go do a good snubber, I can recommend one of those application note like from TI. Yeah, this is also in a good application note wrote what you're doing with this. Normally, if you look on your topology, you will see on the scope, you will see this overshot and ringing. Well, this come from the parasitics leakage inductance, the parasitic of your PCB. It's come from the parasitic or this capacitance from your MOSFET and so on. So what we can do here, this overshot is not so good because the MOSFET could die quite very fast. If you not take care and the spikes are very high, it's not so good. So in this case, what you can do, if you want to measure and you know all these parasitics like the capacity of the transformer and if you know the drain source capacity, you can already, and the leakage inductance of course, you can already calculate what kind of peak you will expect. But actually I don't want to have this peak because that may destroy my MOSFET. So what I can do, like in the ST Micro application I described, you can use this tenor and resistor capacitor snubber, and you will clamp this overshot voltage, which is not, it should be definitive, the value in that way that your MOSFET will not die. So you have to think on this peak and use a TVS or Zener diode to be able to not kill your MOSFET in very, very fast way. If you are trying to do this transformer in different way, if you just take primary and secondary wounded on the bobbin, you have a high capacity coupling. Of course, this is expected. If you are thinking, okay, we can reduce this area of each other, because as soon we reduce area of the capacitors from this to this, it could be a little bit better. Yes, of course, but it will increase the leakage inductance, and also why I should use, if I have so much space in the core, to not use everything. If some people try to do like in this picture on the right side, to make the primary to secondary a little bit more wide, the other one a little bit less wide, so narrow. Okay, it's increasing for the safety distance. Some manufacturers say you need that because in this case the creepage voltage will be better. Yeah, could be a solution, but it's absolutely not good for in terms of EMI and for coupling. But we had another idea. We took, instead of making any voodoo on the bobbin, we split the bobbin cores, the windings actually on the bobbin core, and then we start with the first winding, then stop in the middle, continue the secondary, complete it, and then again finish the primary. So actually it's a sandwich one. And with sandwich one, we have a good magnetic coupling and a quite good capacity coupling. So this is a balance between capacity and leakage inductance. And this is actually what reduce, in fact, the leakage inductance and make the transformer not too expensive and not too difficult to build it. So if we look again on these two schematics and pay attention, both schematics are actually same. What is the big difference of those? The transformer, it works in the same way. The only thing when you realize and looking on this schematic that funny, these dots are a little bit in the opposite direction. Why we should do this? What is the meaning of this dot? Dot means always beginning of the winding of the transformer. Of course, it must be phase shifted, but in terms of function, it will still work the same way. But the big difference, the impact, what you will see is not on the function, it will be on the EMI. We took the same transformer and we make first with a different beginning of winding on the same core, the same bobbin, the same number of turns, and then we make a comparison between when the dot is on the IC, on the switching node, on the MOSFET, or on the hotspot or the high voltage area. And if you look on this same construction, same transformer, you can even read that in a very nice application note or blog. You can see that if you put the dot to this high voltage, in terms of EMI, you make a reduction of the EMI noise. So that's the reason why we say it's a good point to put this dot to the switching node and change the position of the transformer of the beginning of the winding. So that's something which in EMI it's make a good impact. Okay, if you want to filter it and you have no time to make your own filter, you can take different ready-made filter from stock. They are standard in single stage advanced. It means it has additional X cap to the Y caps, and you can have even in a two stage. In the two stage, you have two different common mode choke additional, and they always the Y cap and is always the X capacitor, and you can of course in the size is a little bit bigger because you have to fit in the box two different common mode chokes, and this could help a lot if you want to pass a conductor emission. The thing is, when you use that kind of nice metal boxes with excellent good filtering, you have to take care also they are acting in both noises. They have against something common mode noise, and if you act like a common mode noise, which means on the both on the phase and neutral come the same, absolutely same noise. What is acting in this case is the inductance, the common mode, like a same the name, common mode choke, and you have these two Y caps. In differential mode, it will act also something, but in this case is not the Y cap which is making the filtering. In this case will act the leakage inductance of the common mode choke and the X capacitor acting like a LC filter. But you have a X capacitor on the input. That's the reason why, for safety reason, you need a resistor to discharge this X capacitor, because I had once experience with my wife. I did dry my hair with my hair dryer, and she wanted to use it as well, but in a different places. And I just not switch off the hair dryer, just put it on the wall and give it to her, and she put her finger on the connector of this hair dryer, and she get shocked. And then I realized, oh my God, this hair dryer doesn't have a discharging resistor for the capacitor. Beginning of this point, I have my own hair dryer, and my wife has her own, because she did refuse to touch any hair dryer anymore, which is given from myself. So actually, it was a hair dryer. Maybe the resistor was broken. You cannot put here a very small resistor. This resistor must be, of course, calculated. I will go later on. In regular operation, when you have these two Y caps and the X capacitor, actually, you have to take care about the leakage of these capacitors, because according to a norm, you have to pay attention that on the PE doesn't react your fuse. You have a safety fuse sometimes, and you cannot put too big values here. In the worst case, when it's the neutral line, it's interrupted, you may have even this constellation, and the leakage should be in some limit that you will not broke your fuses. So how to calculate this value, I guess, is not a problem if you're electronic engineer, but for the resistor calculation, it's a little bit more tricky. Now, if you want to have a low leakage, like for medical devices, it's even, we have some filter where we are not using Y caps at all, because Y caps as always have a small leakage of the current on the PE or the protection earth. And then if you choose the filter with low leakage, they have only the common mode show, the X capacitor, but no more Y caps. So you can see here the resistor for this capacitance, and according to the value of the capacitance, you have to calculate the resistance value. And already in this box, you will have the right resistor, uh, not a short circuit, because I guess the short circuit resistor would be the best for EMI because you don't have noise at all. The problem of the function will be, let me see that way, maybe not optimal. So because of this reason, we did put some kilo ohms, which is just enough to discharge the capacitor in case you plug it out, but still making no big leakage and not disturbing your efficiency and making short circuit. Okay, again, the position where you put your filter. Well, if you do a filter in your design, you have a different, maybe purchased switched mode power supply, which you find out make problem in the EMI. What to do? Take a box from Viltroelectronic, connect them together, but pay attention. If you wire that together and you have the noise source coming from the switched mode power supply, you cannot do in this way that you will cross again the cables or put them too close to each other, because you will jump the filter effectivity and you will have EMI problem. You have to place the filter as close as possible. If you have a enclosure like a metal box or something like that, close to the wire where there's entrance or the connector, and then go from the end output of this to the switched mode power supply, and then from the switched mode power supply to your intelligent electronic, whatever we have. This is very often seen that people using this mains filter, and then because of the wrong construction on the schematic, everything work on the table works, but when you go to EMC lab, you make some problem because you put in the wrong place. That again, very often to see this kind of very wrong connection, that you come with a cable, you put the filter and you turn back again, and you have your capacitive and inductive coupling, or into the metal box enclosure. Special industrial electrical guys, they just taking like easy way, just connected to the wall in the very correct way, in the shortest way, but then they route the cable again close by the entrance, and again it's a big problem. So try to do in the construction that you're not crossing or not come close to this area where you have the filtering effectivity, because else it won't work so good. Of course, this different filter will act in different system impedance. We are measuring always in the 50 ohm system impedance, but if you have different unsymmetric system impedances, of course, the filter effectivity looks different. And how to choose the right filter, I will say, if you go to the LT Spice, you will find the models for these filters. I don't know if any other manufacturer offer LT Spice parameter, but we're offering for LT Spice in the library all these parameters, and you can simulate in a different situation. And Mike Engelhardt make with LT Spice a quite very nice tool for design engineer, and you can simulate that even if you are making a good simulation, conductor emission. You can pre-simulate conductor emission without having anything on your desk, and you can see how good this filter are working or not. If you use this kind of filters and you look in the data sheet, we always recommend to make a good grounding. This is very important, to have a very good connection to the ground, and also here by the connection to use maybe not just a wind cable on it, make a good connection to have a good electrical stability. If you want to design your own filter, this is also possible. If you don't want to have a box ready made, you want to be more flexible, you can try to ask our colleague in the sales or on the website. There are different part number for different filters, or you can build your own filter. If you take this box, you have some different PCBs and a lot of Y caps and X caps and common mode chokes from beginning from different material like manganese, zinc, nickel, zinc, or nanocrystalline, and you can use in different interferences to filter your noise. If you want to have also the varistor for over voltage or also fuse, it's also possible. They have just different numbers. More information you can get from our books like Trilogy of Magnetics or also the LT Spice books. And if you want to stay in contact with me, I still have also a LinkedIn profile and also a YouTube channel. If you go to the YouTube and you put Ask Laurent, you will find some nice videos about how to measure common mode choke, whatever, to temperature increasing or for inductance and saturation, so on. Now, I guess Marco from Emser will show you some very nice live measurement with the excellent EMI receiver and with the built-in listen, which I'm really fascinated. I thank you for Marco for this nice collaboration, because I did try a few times to make some measurement and I never imagined to be so fast and so easy with that kind of machinery. So for the question, I will be staying in the chat, and now Marco, the stage is yours.
Thank you, Laurent. Thank you for your interesting presentation and introduction. First of all, can anyone confirm that you hear me correctly and you see the presentation correctly?
Yeah, Michael, we can see it correctly. So yeah, you just can go ahead.
Very good. So my name is Marco. I work for Emser. I handle business development worldwide. Emser is a company based in Barcelona, Spain, which designs and develops innovative EMI receiver with focus on conducted missions. As you can see, the agenda for today, it's really quick presentation and explanation of modal measurements, really 4 slides, and then we will go in the fun and part, which is the real demonstration of our product and Würth filters. Okay, so let me just tell you, remind you on how typical EMC measurements are done. So the standard approach is that you measure only one channel at a time, whether it's line or neutral, or if it's 3-phase, you measure line 1, line 2, line 3, and then neutral. If you use an analog receiver, it takes a life to make the measurement. But most of all, it's not possible to determine the source of the noise. So what do I mean with this? It means that you can measure the total emission of one channel, and which can either pass or not pass. But this emission is composed of common and differential mode, as Laurent was explaining before. And if you don't have the information on how much of this noise is composed of common and which part of differential and in which frequency, you don't know how to design the power line filter, because the power line filter is composed of active components, mainly chokes and capacitors, which have their duty is to reduce a particular modal emissions. All of this, of course, makes it cost-consuming. And this is why we proposed a new approach, which is design your filter by looking exactly at modal measurements. So what is modal measurements? Like modal measurements are common and differential mode. And if you would look at the 2 images that I have here, you would identify the differential mode as the noise that goes through one conductor and comes back in the other conductor in the opposite direction, while the common mode goes in the same direction for both conductor, and so it recloses through ground or through straight capacitances. So you really need to know these 2 for filter design. As Laurent was explaining before, each filter has an action on each mode. And by exactly knowing in which frequency ranges you have, you can really pick the components that you have. Of course, one option is to use the big filters, like the box filters that especially Laurent was showing before. This is an option, of course, but the problem is that, for instance, the box might be too big or too expensive, or simply doesn't work. So your boss might telling you, hey, this doesn't work. It's too big, So you need to increase the size of your UT, or you need to take something out, so reduce performances somehow, or you just need to shut down the project so no one's happy. So if you, I don't want to repeat the slides because Laurent explained it correctly, just to remind you of the effect of each component on the mode. So the choke, common mode choke acts on the common mode noise, while the capacitors, they act more on differential mode, especially the CX capacitor placed between line and neutral. And here I have a zoom in of our receiver, which you will see later on, but it's the frontal part. And this receiver is a double channel receiver, which integrates optionally an internal listen, double channel listen. So as you can see, the lower part is the listen. It's completely shielded, so that's why we have these cables, which are RF connectors, which they go in the upper part, which is the measurement part. We have 2 receivers in 2 channels, 2 receiver with 3 detector each. So you know the standard asks you the CSPR 16, so to the measure with the quasi peak and average. We also have the peak detector. And the black Schuko here is for connecting the UT directly. So my next slide, as promised, is presenting you the demo setup. And I'm changing the camera right now. And I guess Marcus from Wolf has something to tell you so that you can see perfectly what I'm doing.
Yeah, exactly. So as Marco is changing his webinar or his webcam, just a hint for you, you can have also a different view. So when you make your screen from the GoToWebinar in full screen, you see on the header or on the upside, you see a lot of options, and there you can also maximize the webcam. So in this, in this case, it's the test setup from Marco, and you can also just switch between the presentation and the test setup, so you see exactly that what you want to see. So,
okay,
yeah, I think we can go ahead.
Yes. So can you still see my presentation? Am I sharing it?
Yeah. Yeah.
Okay. Yeah. Very good. So you can see that in the left part, we have our UT, which is a switching mode power supply. This UT goes through a filter selection box. In this filter, we have in this box we have 4 positions. We have connectors and 4 positions. The first one, the number 4, it's without nothing. So it means that this position goes directly to the receiver. So it goes into the listen and then it's measured. So we measure the emission of the UT without anything. And then we have 3 positions where we put filters, and we put really a big filter in the box that Laurent was showing you. Then we put a small filter still in the metal box that you saw before. And then we put a PCB where we designed our own filter thanks to the information that the EmScope can give us. And you will see right now the effect that this has on the noise and on the filter size and cost. Okay, so my presentation is done here, and right now I will change in the software. So let's see, I can do like this, and I can do like this. So can someone confirm me that you are seeing the software?
Yeah. Yeah,
perfect.
We see it.
Perfect. So this software, it's embedded inside the instrument. Just wanted to tell you that it's free. No updates. All updates are for free. Just wanted to say, because it's something that doesn't happen in EMC. You usually have to pay a yearly fee, maintenance. This doesn't happen with the software inside the EmScope. As any other software, you can go in device configuration and set all your parameters, which is color, whatever, update device for free. I've done it for you, and I will explain later on how I will use these settings. So on the left, you see a menu, top to bottom, and you would use this menu to configure all the measurement that you have to do. So for instance, the frequency band, it's already here, so I can just select it and I can modify still the start and stop frequency. So according to the CSPR, I don't even have to know that the resolution bandwidth 9 kHz. The software does it for me, and I can set the dual time and sweep mode. Okay, so in amplitude, you can take into consideration external losses and internal listen. Since I'm using the internal listen, I'm already compensating it. Okay, the thing that I wanted to quickly explain you is how this trace configuration works. So as you can see, right now, I have this menu, which is opening, and I've selected a few things here. If you see, the clear bright option has a different color. It means that I select this one. If I go down, I see that I'm selecting EMI measurement. I'm measuring the line with respect to ground with the quasi-peak detector. And where do I see this information? I see this information here. Trace 1, line, quasi-peak, and I'm clearing. And the color is blue. So this is my measurement. What does this plus here allow you to do? If I click on this plus, I will add another tab, like think it as a Google Chrome tab, for instance, but you will still see in the same page the measurement that you were doing before. And this is used for comparison for multiple measurements at the same time. So for instance, you would see that here, the software is opening a trace 2, a red color. I'm measuring the line with the peak detector, and I'm clear. Clear means that every second, because I set the dual time at 1 second, it's measuring. It's an FFT receiver, so the measure, it's really fast. In 1 second, I'm measuring from 150K to 30 mega. I don't care about peak detector because the standard asks me to measure with the average detector. So the limit is with the average. Some of you, if you have all the analog receiver, you have to do the measurement with peak, scan all the band, and then go back with the quasi-peak detector. This doesn't have to happen with EMSER. So right now you see trace 1 and trace 2 with the 2 colors. I can still open other tabs because, as you can see, the receiver has 2 channels. So it means that I'm measuring the line, I'm measuring the neutral, and I'm measuring them simultaneously and with 3 detectors each. So I could, for instance, just to show you, open another tab, click the neutral, and put the quasi-peak detector. And I can open another tab, add the neutral, and the average detector. So right now, in 1 second, you have the measure on the line, neutral, with peak, with quasi-peak and average detector. Okay, this was just to show you. Now I will close the last 2 tabs and work on this. So as you can see, we are clearly above the limit. I can also check it with our in our function of list of maximum emission. It will mark me all of the emissions here, all the points, but I clearly see that I'm failing the EMC test. So I have to do something. The common thing is that you use a power line filter. So first of all, I'm going to save these measurements if I want to see them later. And I will write quasi-peak and average with no filter. You can save in different options. I'll just use the CSV file and save it. And later on, we will compare. So right now, I will just do what commonly is done in the wrong way in EMC. So just put a big filter and see if it works. And I will do it in real time. So now you see my hands here, and I'm switching my box, and I'm putting the big filter. Okay, so if I put the big filter, I can see that I pass. So my test it's completed. I can go to my boss and say, hey, I passed the test, our product can go. And then I can incur in the problem that the filter is too big, cannot be used, or it's too expensive, or whatever problem you may get. So what is the good way to test EMC? It's to go back in when you have the product without filter, and I will do it right now. And as we were explaining before, perform modal measurements. I guess you are seeing real time how fast this instrument is. But also now you will see the really interesting function, which is modal measurement. So how do you perform a modal measurement? You just click here in modal, and you just click common mode. So now here, check my mouse, it says that the trace 1 is measuring common mode with a quasi-peak detector. And now I'm going to trace 2, and I measure the differential mode with the quasi-peak detector. Okay, so I can see right now that my emission is composed of both modes. Sometimes it really happens that you have one mode at different frequencies, so you would need different components to filter. But right now, let's say at lower frequency, I have lots of common mode. I have really high peak of common mode, and then differential mode. So I will save it just so I have the measurement if I want to upload it later. In 1 second, I save it. And then I will do another thing that the program allows me to do, which is the freeze option. So I freeze this trace, and I freeze the trace 1 as well. So now I have both modes frozen. I'm opening another tab, and I want to measure the common mode, the differential mode with the quasi-peak detector. And then I want to measure the common mode with the quasi-peak detector. So what have I done here? Here I've frozen 2 traces of what the UT is emitting, and I opened 2 traces which are measuring. So right now, if I change the filter and I put the filter big filter, I will see its action on the both modes, and then we will compare real time. So now I go back here in position 1. Now it's difficult to understand, but I'm using another function of the MScope, which is this high here. I can hide the trace. So for instance, I'm adding the differential mode and the differential mode. And now you see why I changed the color of common mode blue of the frozen, so it means UT without filter, and common mode red means UT with filter number 1, big filter. So I can see that I have a good reduction at high frequencies of common mode, but at lower frequencies, so and so. Yes, I have a reduction, important reduction, but you always have to take care that this is a measurement that is done not in a screen environment. So maybe I can have something that it's coupling or whatever. So I'm not so far from the limit, and measurements of common mode especially are highly affected by the setup, by ground connection. So I will have to do something more. Just since we are here, I will hide the common mode and show you the differential mode. So now I have differential mode in red, the one not filtered, and in differential mode in blue, the filtered one. So I see this is really good performances of the filter. For differential mode, I have no problem. It's really good capacitor, I would say. So now what can we do? I will hide everything, and I will close my last traces. And I will, I will leave these traces on, because what I want to do is put the second filter. So the second filter is a small filter, like in the box, in the metallic box, but smaller. So smaller means less space in your UT and maybe less expensive. So let me change it in my box, and we will check the results real time. And I will use the function still of hide the noise. So now I want to compare common modes. So I hide the differential mode and I hide the differential mode. So now I'm comparing common mode and common mode, filtered and without filter. So I can see still a better reduction, really better reduction than the first filter. There are 15 dBs more of reduction at this frequency, 170 megahertz, which was the point that it's giving me problem. But if I check the differential mode, I will see something unexpected. I will see that the differential mode is higher than the one before. If you remember, so the red trace is the differential mode without filter, while the blue is the differential mode with filter. And if you remember before, this was really low, but with this filter it's not so good. So basically, the total, the conclusion is that these two filters are basically giving the same attenuation, but I'm not really improving anything. So if I close everything, for instance, and we'll do a measurement of EMI in 1 second, I upload, I go in EMI, I put the line with a quasi peak, I would say that it passes. And this is with filter number 2, the small filter. I'm freezing it, I open another one, I measure the same with a quasi peak, and I put the filter number 1, the big filter. So you see the total, the difference in emission, in the total emission that these two filters gives. So you would see, apart than this peak here at 200 megahertz or less, 200 kilohertz, sorry, it's practically the same. And here, well, something at 400, 700 kilohertz, it's giving more attenuation, the red one, but still not so much, not so valuable. What should I do? I should do what it should really be done. Design a filter, use the filter kit of Würth, and really solve your problem. So for instance, I go in clear and bright, and I do the modal measurement with the common mode. I open another tab, differential mode, the quasi peak. Now I put the configuration again without the filter. So I have the noise here, the total noise. I'm freezing this one as I did before. I open 2 more and I measure the same. And now I'm putting the filter number 3, which is my PCB and my filter, my design filter. So what do I see? I see that if I keep hiding, for instance, and compare 1 to 1, I have huge reduction in common mode, really huge reduction at the lower frequency. Still, I have, let's say, 60 dB reduction. And also in differential mode, let me unhide things. In differential mode, I have huge reduction. Basically, you're taking out all the differential mode. So the differential mode is not reaching the receiver at all. So this is for instance, a smaller filter, a filter with less components, but a filter with better performances. So if I close everything again, and let's see, I'm okay with my modal emissions. I go to EMI measurement, I go to the line, and I measure with the quasi-peak detector. I open another tab, I measure with the average. This is okay. And that's it. I have, let's say, 40 dB difference. I'm sure that when I go to my EMC lab for my final stamp on the product, I pass. I have no surprises. I put a filter which is perfect for my power supply, for my UTs. I put a small filter, I mean the most optimized in its size, and I put the most one optimized also in price. The thing that this instrument allows you to do, it's really to set the goal for your filter. If your goal is to minimize the size, then what you have to do is take in smaller component and maybe with better performances. But if your target is price, then maybe you allow bigger components which are not so good in performances. But still, you need to make sure that when you go to the EMC lab for the final stamp, you pass. If you get a fail, you've just lost time, money, and spent a lot of time for solving your problem. because if you try to solve an EMC problem without knowing common differential mode and do a real-time comparison, it takes really, you enter in a loop of trial and error, and you will never come out of it, or you come out with the best solution. And the last thing that this software allows you to do, it's a nice report, a PDF report, which basically you can show to your manager and say, hey, this is my work with my optimized filter and with the results. And of course, you put your company logo, write whatever you want, and you have the graph. Of course, this software allows to do lots of things more as waterfall function. It's not the object of this webinar to show it, but with one click you see the waterfall function, so the time the time frequency diagram. But still, the really major point of MScope and the advantages that brings are focused on modal noises, which are the only components that you need to look at when you design a filter, and especially if we wanted to make it small, optimized, and with good performances. Okay, this is the end of my presentation. Thank you very much for your time. I guess now Marcos will take back control, but please feel free to ask us anything, visit our website, and be in touch. Thank you.
Attached images are available in most podcast streaming networks. You can find the entire line of Würth Electronic line filters available at Würth Electronic Online. This podcast was taken from an updated Würth Electronic webinar. To view the materials and replay the webinar on demand, visit our website at www.we-online.com/webinars or click the link attached in this podcast. You're listening to Würth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Electronic technical specialists. We're going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Electronics What's Up podcast.